Hello and welcome to this screencast which explains how to work out whether a chiral molecule is of the R or S configuration. Some molecules can exist as left-handed and right-handed isomers. This happens when a molecule contains a carbon atom which is attached to 4 different groups. If this is the case, the molecule will not contain a plane of symmetry. We call the carbon with the 4 different groups attached a chiral centre, or sometimes an asymmetric centre. Molecules like this exist as two non-superimposable mirror images of each other, in other words, left and right-handed versions. We call these types of isomers enantiomers, or optical isomers. Here's an example of this. The molecule shown exists as right and left-handed isomers due to the 2 possible orientations of the attached groups. These isomers are mirror images of each other. However, if you try to put one on top of the other, they would not match. In other words, they're non-superimposable. You can try this with your hands to see how it works, as they're also non-superimposable mirror images of each other. Here's an example of a real molecule, 2-bromobutane, which exists as 2 enantiomers. We can identify the chiral centre in 2-bromobutane, and the convention is to mark it with an asterisk, as shown. We need a way to describe isomers of chiral molecules so that we know whether we're talking about the left or right-handed isomer. For this, we use the Kahn-Ingold-Prelog or CIP sequence rules. Let's look at one of the enantiomers of 2-bromobutane from the previous slide. Step 1 is to look at each of the atoms attached to the chiral centre and give them priorities based on their atomic numbers. A common mistake which is made at this stage is to add up the atomic numbers of the whole groups attached to the chiral centre, not just the atoms. The atoms are numbered from 1, highest priority, highest atomic number, to 4, lowest priority, lowest atomic number. If there's a tie, for example, if there's 2 carbon atoms attached to the chiral centre, then you need to look at the next atom along in each case. The carbon attached to the atom with the higher atomic number gets the higher priority. Next, the molecule must be orientated so that the lowest priority group, number 4, is pointing away from you. You'll need to make sure you know what wedge bonds and dotted bonds mean to be able to do this. If you have trouble picturing the 3D shape of the molecule, which a lot of people do, then you can use molecular modelling kits to actually build the molecules until you get the hang of it. I'm going to show you how to rotate the molecule using a chemistry drawing package called ChemDraw. At the moment, the bromine atom is pointing forwards, the methyl group is in the plane of the paper, and the hydrogen atom is pointing backwards. Therefore, we don't need to adjust this molecule much. When you have the molecule orientated correctly, the final step is to draw an arrow from group 1 to 2 to 3. If this arrow goes clockwise, then we call the isomer the R enantiomer, and if the arrow goes anti-clockwise, then we call it the S enantiomer. You can remember this because the arrow follows the shape of the letter in each case. This molecule is the R enantiomer of 2-bromobutane. Here's another example. The first thing to do is to identify the chiral centre. Next, assign the priorities to the different groups. Fluorine has the largest atomic number, 9. Nitrogen is next with an atomic number of 7, carbon is 6, and hydrogen is 1. Now the molecule needs to be rotated so that the lowest priority group, the hydrogen, is at the back. It might help if you would redraw the molecule at this stage, as other groups will also change position. The last step is to draw the arrow from the highest to lowest priority groups, ignoring number 4. In this case, the arrow is going clockwise, so it's the R enantiomer. Here are some more practice questions. The answers are shown on the next slide, so you might want to pause the screencast while you have a go. Thanks for watching, and look out for more resources coming soon on the Foundation Chemistry Tutor channel.